Hi, and welcome to Module 6, the last module in Lecture 15. Here, having in the previous module gone through and provided a methodology for computing optima of constrained optimization problems that utilize inequality constraints, we're now going to give a couple of relatively simple examples for how to use the method in practice. Slightly more complicated examples exist in the book, and you can also see examples in the problem sets and the problem sessions and such. Okay. So let's get started. The two examples here, the first one utilizes a single constraint, the second utilizes two constraints. The first is sort of a budget constraint type of situation, the second is are two non-negativity constraints. In the book, there's an example which puts those both together to have three constraints. Now, note first that each of these functions is concave, therefore, and the constraints are quasi-convex, and therefore, the Kuhn-Tucker theorem says that we will have maxima should we find them, so that's good. So let's get started and actually go try to find them. Okay, so let's do the first one first. We'll do that one in blue. Okay, so step one, we're gonna set up all of our constraints in the form that we need to. So the form is that h is less than or equal to 0. So our constraints would be h equals 2x plus y minus 10 is less than or equal to 0. There we go. Step one. Step two, we're going to form our Lagrange type function. So here's the objective function f first. And this situation applies to something like two individuals have complementary actions. So the more x I do, the more y is good for you. But they both have costs that are convex. So the combination is a concave function. And now we're going to subtract, right? Because we're doing a maximum here. These are both maximization problems. There's only one mu, so I'll leave off the subscript. And that's going to be times h. Okay. So there we go. Now we have our Lagrange type function. Now we'll have to get our Kuhn-Tucker conditions. I'm going to combine a couple steps, 3 and 4 here together, to do it all at once. Save some space on the screen. So first we're going to differentiate our function with respect to x and y. So x first, we get that equaling y minus 2x. Now forget the mu over here, we have 2 mu. And that equals 0. Next, we're going to have the, that's an x by the way, there's a y. We're going to have x minus 2y is the opposite, minus just mu equals 0. Those are the stuff that comes from the differentiation. Now there are no equality constraints, so we don't ignore lambdas, but we do have a mu here. So we have one complementary slackness condition that looks like so. There we go, and that's going to equal to 0. That provides us with two cases, which we're going to do. Step 5, case 1, or case A, or whatever. Case A is that mu is equal to 0, so our constraint does not bind. So our constraint does not bind in this case. So that implies 2x plus y minus 10 does in fact be less than 0 by itself, and we have to have mu equal to 0 to get rid of that constraint because it does not bind. What happens then? Well, equation I, 1, little 1, and little 2. In that case, little 1 implies what? Well, if mu is 0, then we have y equals 2x. And little 2 implies that x equals 2y. And put them together implies y equals 4y, or y equals 0, which implies x equals 0. Now, it is true that 2 times 0 plus 0 minus 10 is negative 10, which is less than 0, so the constraint does not bind in that case. So this is a possible outcome, 0, 0, with mu 0 as well. So here's a possible outcome of our maximization problem, all zeros. Not a very supportive group here, right? Next example, mu is greater than or equal to 0, and the constraint binds. Now we have a couple of equations here. This constraint implies y equals 10 minus 2x. Then in that case we can plug in Oh, sorry, and then is a better way. Yeah, so then 2 implies mu equals x minus 2y implies mu equals x minus 2 times 10 minus 2x equals what? That's plus 4, that's 5x minus 20. And therefore 1 implies, we plug in for y, we get 10 minus 2x, that's y. Then we subtract 2x for the x, I'm up here by the way, and 1. And then minus 2 mu, mu is 5x minus 20. That's going to equal to 0. That whole thing, we have a 10 over here, we have a 40 over here, that's 50. We have minus 2x, minus 4x, minus 14x. That implies x equals 50 over 14, or 25 over 7. That's a possible solution. Looks better than 0. Let's check it out. What does that imply? We can plug in for y over here. 10 minus 2 times x is 10 minus 50 over 7. 10 is 70 over 7. So 70 over 7 minus 50 over 7 is 20 over 7. So that implies y is 20 over 7. And to be complete, mu therefore is, where's mu? Mu is x minus 2y is 25 over 7 minus 2 times 20 over 7, which is 40 over 7, is negative 15 over 7. Uh-oh, we're in trouble now because mu must be positive. So we've seen that this cannot be an example, despite the fact that we might prefer to have 1x be 25 over 7 and 1 be 20 over 7, which means both people are actually participating to this complementary action. Our mu here is negative 15 over 7, which violates the assumption that it's greater than or equal to 0, and therefore this is not, case B is not a possible case, not a possible maximum. And you could check that by plugging in if you wanted to. 25 over 7 times 20 over 7 is would be on top here 500 over 7, but this, sorry, over 49, apologize. Whereas this thing by itself is 525 over 49, and this is 400 over 49. So this is way less than 0. Whereas if you plug in zeros everywhere, you get 0. So actually, it's not a maximum anyway. So we find if you're doing this whole thing is only one of the two cases produces a maximum. It's the first case, and the actual maximum here is 0, 0. So and the budget constraint does not bind because no one wants to spend any money anyway. So there you go. Here's the first, or do any effort anyway. So there's the first example. We see we went through, we constructed, we set our constraints in the proper manner. We constructed our function, a Lagrange type function. We found our Kuhn-Tucker conditions. We solved the system of equations, dealing with each case for the complementary slackness conditions separately, and we found one and only one maximum of this example. There you go. Okay, moving on. Next one. We'll do this one in green to be different. So this one's all separable, so it should be a little easier in that sense, but it has two conditions, so there'll be 4 cases. Let's start again. First, we have to set the conditions into the so that it looks like h is less than or equal to 0. So h sub x for the x1 is going to be equal to negative x, which is less than or equal to 0. That's our first condition. So we have to make it less than or equal to 0, which means flipping the sign on our thing we're given here. And then hy, that's step 1 by the way, hy is equal to negative y, which is less than or equal to 0. There we go. So, 2 conditions. Step 2, form our function. Well, first we have f. I'm going to put the x's together to make it slightly easier. Now we have 2 conditions. It's negative mu x times h. Here h is negative x. And then it's negative mu y times hy. But sorry, that's just y. It's negative y. Put the plug in there. Negative y. And there you go. That takes care of our function. Again, we'll do step 3 and 4 together. What happens there? And again, one more time, I've said this a bunch of times recently, I'm going pretty fast here. But the beauty of the video is you can pause and stop, make sure you understand every step before you move on and just talk some more too fast. So there you go. So 3 and 4. First we're going to differentiate with respect to x and y. So the x1 is going to be 3 minus 2x. Don't forget the mu over here, plus mu x equals 0. The y1 is going to be negative 3 minus 2y plus mu y equals 0. And the plus is because you have a negative y as your h. Now we need the two complementary selection conditions. Mu x times x equals 0. And mu y times y equals 0. Now you can take a negative out front if you wanted to, but it's equal to 0, so it doesn't matter. Okay. We get 4 cases from this. So step 5 involves 4 cases. I'm going to write them up here so I can do the math down there. First case, case A. Case A has mu x equal mu y equals 0, which implies that x and y are both strictly greater than 0. Okay. Case B has mu x equals 0, mu y greater than or equal to 0, which implies that x is greater than 0, but y is equal to 0, because the constraint binds for y in that case. C is the opposite, so mu x is greater than 0, is greater than or equal to 0, mu y is equal to 0. And that implies x equals 0, y is strictly greater than 0. And finally D, they're both greater than or equal to 0, and x equals y equals 0. Those are our 4 cases. Okay, let's box this off so we have room to do things. Okay, case A first. We'll just go in order here. Case A, they're both positive, all the mu's are 0. Well, in this case, and I'm going to put little 1s over here again. 1, 2. In this case, 1 implies x equals 3/2. So far, that's fine. That's positive. And 2 implies y equals negative 3/2, which it can't be because case A assumes y is strictly positive, so that's not 1. Next one. The next one implies, B, not 2. B. So for B, we have y equals 0, and x is positive. So 1 again implies x equals 3/2, no problem there. What does 2 imply? Well, 2 implies that, now y is 0 here, so you have mu y equals 3. 3 is greater than 0, so that's fine. We assume that mu y is greater than or equal to 0. It is. So this is a possibility. C. C, we have x equals to 0. So 1 implies mu x equals negative 3. That is not greater than or equal to 0. So this we can stop right there, and this is not a possibility because we violated the assumption that mu x was greater than or equal to 0. So that's not 1. We have 1 more to go. This last one over here. D now. Now we have mu x and mu y positive. All the x and y are 0. And again, in that case, 1 implies mu x equals negative 3, which violates the same exact reasons. We assume that mu x is greater than or equal to 0. We're done. We have exactly one of the 4 cases working as a possible maximum. So the maximum here is 3/2 and 0 is the only maximum here. And just for completeness, mu x is going to be 0 and mu y is going to be 3. That's it. We have a single maximum of this equation, and you can probably see that by looking at it, right? All the y's are negative, so just increasing y just makes your utility work, your function makes it smaller. So you can maximize that function at 0 for y, and that's going to bind. That's why I chose it that way. Whereas x, you can have an interior maximum that's greater than 0. But there you go. That was very quick, But I hope that shows you how you do this technique. And again, there are more examples in the book and more in the problem sessions and problem set. That's it. And that covers the end of the lecture on multivariable optimization. If you've gone straight through, I bet you never thought you'd be doing multivariable optimization by now. But that's it. And we have only one more lecture left. The last lecture covers comparative statics and implicit function theorem, implicit differentiation. It's a short one. That's it. Thank you very much.